Hello and welcome back to the Hyperthesis. We are at the episode 91, and today we also have a very special guest, Mayukh Bagchi. Welcome. My name is Feely.
I'm Liam. And I'm Patrick.
All right, as you can hear, we have Mayukh here with us to talk a little bit about astronomy stuff. It's been a while since we have an astronomer in the podcast. So a little bit of Mayukh's background. He's doing his PhD in astronomy and instrumentation here at Queen's University, and he built radio telescope for balloon-borne experiments. And he also did complete his master's degree at Queen's too, designing instruments and analysis methods for millimeter and submillimeter astronomy. He completed his bachelor at the SRM Institute of Technology in Tamil Nadu. So welcome, Mayukh.
Yeah, it's nice to be here, and yeah, I'm excited to chat about radio instruments, ballooning, and what like our goal is with building radio telescopes from a balloon and seeing what exciting science we can do with it. Mhm.
Nice. So the intro topic for today, I guess we pick a fortunate timing for, well, in terms of year and month, because as the time recording, I think tomorrow is going to be 100-year anniversary that we found out that the Milky Way is not the only galaxy in the universe, and which is like, I didn't know that it was this year, and it's actually this month, November. And this episode will be released in December, but if you backtrack a little bit in last month, November, we are now. So on Sunday, November 23rd of 1942, and this article was published in the New York Times about Dr. Hubble confirmed view that their island universe is similar to our own. So he basically found the spiral nebulae, and turned out those are stellar systems. So the American astronomer, Dr. Edwin Powell Hubble, actually, I think they spelled his name wrong on the article, like Hubble. It's kind of hilarious. But found that two spiral-shaped nebulae, I don't know if I pronounced that right, but the plural of nebula, objects made up of gas and stars, which we thought that they were in our Milky Way galaxy, were actually located outside of it. I'm not sure about how the method that found that out, but those objects were actually the Andromeda galaxy, as we know it. I think the closest large galaxies near us, and the Messiah 33 galaxies. So just a little bit of news, old news. And another topic I want to raise up is that we like to think that our Milky Way is like the standard galaxies, and like a very typical galaxy. But these new studies, I think it was published this month, they provide some evidence that the Milky Way is actually one of more anomalous galaxy if you think of its formation. So I'm talking a little bit out of my waters here, so I'm not sure too much about this, but so there is this group that after more than a decade of scanning using this satellite ground galactic analog, or SAGA, it's a survey team that look around for galaxies that are like the Milky Way. So the result that was published on November 18th in the Astrophysical Journal showed that the evolutionary history of our Milky Way is quite different than the other galaxies with comparable size. So it showed that the galaxy formed inside this region of dark matter called halo. So this dark matter is not visible in the visible light spectrum, and apparently has a really large size, which create gravitational force that pull ordinary matter from space and transform into stars and galaxies. But I don't think we have like the complete understanding on star formation yet, but the key objective of this Saga survey is to determine how these type of halos, dark matter halos, impact galactic evolution. And what they're trying to look at, they looked at so far, is those galactic satellites. So there are those smaller galaxies that orbit larger galaxy like the Milky Way. And it turns out four of the Milky Way's brightest satellite galaxies. So these are, they're not exactly like other ones. So the galaxy with comparable size to Milky Way usually have more satellite galaxies. So it begs the question that, like, well, how does Milky Way form? Maybe the formation of Milky Way is not exactly like the other galaxies. So we shouldn't use Milky Way as like the standard form. If we want to study galaxy formation, Milky Way is a one anomalous instance. It's not the entire picture. So, Mayukh, do you know anything about these?
Sure. I will say, though, I don't think about galaxies on a daily basis, but since you touched on this topic, which is quite interesting, is actually Hubble's initial discovery, right? So, what he initially thought was a nebular structure, so nebular here meaning cloudy, right? Was actually turned out to be M33, right? Which is the Andromeda galaxy, which is our nearest galaxy in the local group. So local group, as in it's a group of galaxies that are kind of gravitationally bound with each other. So the cool fact that he and later on that we started noticing is that galaxy appears to be blue shifted, right? And what that means is basically when you look at it, it looks bluer than it usually should look like, meaning that it's actually on a course towards us, right? So Andromeda galaxy and Milky Way would probably collide in the next, I don't know, 4 billion years from now. And so right now they're sort of gravitationally bound towards each other, and one is moving towards the other. So when you observe it, you see the wavelengths of light kind of squeezed in together, right? Which causes them to be more blue shifted. So that's one thing I find really interesting. And I know there are people in our department who are actively studying galactic mergers. And of course, we won't be there. Maybe humanity won't be there at all to witness this. But in 4 billion years from now, Milky Way and Andromeda will collide with each other. And that will be quite spectacular. So yeah, that is one thing I wanted to just splurge in there.
Yeah, you also see these really cool like simulations, or I don't
That's
know
right.
if it should be called simulations, but it's like these videos that people put on
No, they
YouTube and
are.
stuff.
You're
Okay.
right. Yeah, they are actually, if not super realistic. I mean, of course, the idea is to make them to model those as realistically as possible, but
Mhm.
it's hard because if you try to include all of the physics into one
Yes.
simulation, you probably do not have computational power to do that anyways. So yeah, there are some simplifying assumptions to it, but they are on a large scale pretty good approximations of what would end up happening. And yeah, they look pretty cool actually when they merge together.
Yeah, but also you see it's like what our perspective would be on Earth, and you start seeing this galaxy just getting bigger and over like, millions and billions of years, and what it'll look like just before collision, and the whole night sky is like lit up with it.
Lit up.
Yeah, it's really cool.
It's really cool.
So one thing I heard was that when they have collision between two galaxies, one could imagine, intuitively, like all the stars kind of hit each other. But apparently, there's so much space that like almost like no collision. It's almost mathematically, it is possible, but the odds is extremely low. Even though there are like millions of stars, of these billions of stars in each galaxy, when they merge, they apparently don't even collide.
Absolutely, you're absolutely right. So the reason why galaxies look kind of populated are because they are really huge and they almost appear point sources to us. But if you really probe inside them, they are not that dense, right? The average separation between stars is a lot. I mean, the closest star to us is also like 4.5 light years away from us. So that's a big distance. So if you imagine that's kind of the average distance between stars in other galaxies too, if not more, right? So when they actually collide, contrary to what you would think intuitively, that is you wouldn't see stars like left and right colliding with each other. There's just so much empty space that they would probably just phase through each other normally, and you wouldn't notice but what would happen, and what kind of Liam mentioned, is the night sky would probably, like, you would see many stars now, because now it's not only the stars in our own galaxy, but it's also stars from Andromeda that'll shine the night sky. So things will get pretty bright. So yeah, there won't be any collisions. But the other thing that is worth mentioning here is, our sun is, I think, 6.5 kiloparsecs away from the center of the Milky Way. If our sun were to be much closer to that, then due to the interactions of the supermassive black holes at the center of these two galaxies, there could be a possibility that our sun would be slingshotted away from the Milky Way galaxy. And that's pretty common to stars that are close to the center. So that could be a dramatic event, but I don't think our sun is that close enough for that to happen. But yeah, this is beyond what I think about on a daily basis, but it's undoubtedly fun to chat about, I think.
Yeah, because I work in the astro wing, basically. Most of the people, and
Yeah.
on my office wing, astronomy, and I hear a lot.
Mhm.
Well, we have thin walls, so I hear a lot of astronomical research, and I was like, well, I don't know anything about these, and I feel like it's vice versa, where we are
Uh-huh.
talking about crystals and self-assembly. They're like, well, we don't do that either. So
Yeah.
that's basically the little short intro topics for
Mm-hmm.
today. So we want to get into your research, and could you tell us what you do?
Sure. So right now, if I had to kind of simplify as to what I'm doing, is basically we are building a radio telescope, and the idea here is to do VLBI from a balloon. So VLBI, for those of you who do not know, is called Very Long Baseline Interferometry. It is a technique used in radio astronomy to get really high angular resolution on the sky. And the reason why, and this is important, is this is how you actually make beautiful pictures of distant objects. Such stuff would not be possible otherwise, just by looking through a single dish telescope. So for example, the famous black hole image that I have on my shirt, that was actually taken using this technique called VLBI. So
yeah, we've
yeah.
talked about that image before for sure, and how they kind of like
Mhm.
turn the Earth into a big radio telescope
That's
by
right.
patching together a bunch of little ones. Which
Yep.
nice little documentary on Netflix about that.
Uh-huh. So what we are trying to do is, we're trying to show right now, it's more of a tech demonstration, that you can actually also do VLBI from a telescope that's on a balloon. Now, you might have follow-up questions as to why from a balloon. Is it just because that's fun to do? Well, yeah, it's fun to do, but there's also a lot of novelty that comes along with doing building such an instrument and doing VLBI from a balloon. And I'll just go in that briefly right now, and you can ask me questions later. But the two main novelties that you can get while doing VLBI from a balloon is, number one, balloons actually fly in the stratosphere, right? And that already means you're above 99% of the Earth's atmosphere. Now, why is that beneficial? Is because you can now access really high frequency light that is coming from these regions around supermassive black holes or galactic center, which you otherwise would not be able to do from the ground. So our Earth is kind of like a filter. It doesn't allow really short frequency waves to come in. There's a lot of water in our Earth's atmosphere that kind of blocks away all of that light. By doing science from a balloon, you can access all those frequencies. And that's point number one. Point number two is, as Liam kind of mentioned, is you're trying to patch up a lot of small telescopes in order to emulate a large dish. Now, imagine you're on a balloon, and your balloon is kind of free to move wherever it can go. So essentially, you're filling in those places very differently, which you otherwise would not be able to do from a ground telescope. So those are the two key novelties, and they can play a quite important role to make VLBI even better. So that is kind of the gist of what I'm doing right now.
Okay, because I would guess so, because if we gonna send a telescope on the satellites, right? We're gonna
Mm-hmm.
it's launching it is expensive, man. How do you
Mm-hmm.
even bring it down? You have to make it, put a thruster to make it fall down, and it will get burnt up in the atmosphere. And I think there's a lot of economical reason to use balloons too, and also like to make the orbit geosynchronous, or or the opposite, right? Or stay still is
Mm-hmm.
really difficult. So in a sense, balloon just use the air to just suspend it. But one of the thing that I'm concerned, or maybe you guys probably know a lot more about these, is like how stable is it? Because up there, the wind, even though the atmosphere is not that much, turbulence. How do you have to deal with those, like gyroscopic um, a device that deal with that?
Yeah, for sure. So again, I think what you said makes a lot of sense, and I'll kind of give you an example as to, for sure, like doing astronomy from space is great because it's the most pristine environment you can get. There's no atmosphere at all. You can access all sorts of frequencies and wavelengths, and that is why you have the James Webb right now taking beautiful, gorgeous astronomical data because it is far away from Earth in a very different space, right? But those are like billions of dollars worth of experiments, like, and that's not easy because you can't ask for billions of dollars just for a space mission every year. On the other side, balloons, they can get you pretty good quality of data, if not as good as what James Webb would give you, but pretty comparable. Uh, at a fraction of that cost. So a typical balloon mission would cost you anywhere from $10 million to, I'd say, $20 million, adjusting inflation right now. And that's like almost a fraction of what James Webb or Hubble or Spitzer would cost you, right? So that is a beautiful trade-off. Yeah.
Is that like per balloon mission, or is that like, it comes down and assuming nothing's been
No,
damaged, you recycle it and send it back up again? And
that is per balloon mission. And the other good part about ballooning is, yeah, you could recycle a lot of your stuff, right? Of course, there's a risk if is basically when it comes down, it can crash and you can lose a lot of your instruments. But we are developing methods to control that landing and control that crashing so that you can still reuse some of your components. But yeah, there's that risk. But even then, it's way more cheaper and also environment friendly that way because you can keep on recycling your instruments, so on and so forth. Now,
Right,
continuing
because
on,
James
yeah,
Webb, they're not planning to retrieve it, right? That's
no, I
goner. Like
think once it's
Hubble, James Webb.
exactly once it's end of mission, it'll probably they just will leave there
Yeah,
to float around and
because like any recycling is better than
mhm,
none, right? Like even you can
exactly.
salvage, you use metal from
Hmm.
it is fine. It's better than shooting it out into space.
Yep. I mean, space junk is a real thing, and I think we all have seen those scary images of how much junk we have placed in our orbit. And yeah, I'm for sure if you're not dismantling or if you're not planning to plunge it into the earth, it'll keep floating there for as long as it can, right? But yeah, but the other cool part about space is everything is very predictable there, right? The orbits are Keplerian orbits. We have very good math that can predict each and every next motion that the satellite will take. And that simplifies your life so much. But on a balloon, that's absolutely not the case because A, you do not have any control on where the balloon will go next. And also, as Feely kind of mentioned, even though it's high up above a lot of the atmosphere, but there's still winds up there. And to give you a context, those winds are about like 5 to 10 meters per second. So they're not super gentle. I mean, there's still some oomph to them, right? So that can actually steer your balloon to different directions. Plus, then there's turbulence that also doesn't help. So, like, I mean, for other missions, that might not make their lives much difficult. But for us, if you're planning to do VLBI, that might make you that absolutely will make our lives miserable in the end when we're analyzing data because there will be all those drifts and all the phase shifts in the data that we'll see just because of the fact that our balloon is not stationary. Like on the ground, that is why you have telescopes mounted on the ground. Like you give it a stable platform, but from a balloon, you cannot. So yeah, the big part about our mission is we need to come up with plans as to how to get around all of these problems, right? So yeah.
So yeah, so think about more of like the instruments of the balloon. These are
Uh-huh.
not hot air balloons as people usually
No,
see,
they are
right? Are
helium
these
balloons.
helium? Oh, so
Exactly.
that's why it's so expensive.
Yeah,
Are
they are
you?
super
Yeah.
expensive. But again, like way cheaper than a space mission. So to give you a little bit context, these balloons are actually pretty thin, right? So imagine a sandwich bag where you would just carry some sandwiches. That is exactly the kind of thickness the balloons are made of, and you just pump it with helium air. And the we are actually flying with the Canadian Space Agency, so they are providing the balloon, they are providing the platform. We just are building our experiment and bolting onto that and doing our science. But NASA, for example, if you fly with NASA, then you have to build your own platform as well, your own gondola. So the Canadian Space Agency, they give you everything. And those balloons, mind you, can get really big, like as big as a football field. So they're huge because they're carrying payloads of like 500 kilograms. The NASA ones, they carry even more, like 1,000 kilograms or 1,500 kilograms. So they're huge balloons. And
They're
yeah,
like an
but
airship.
yeah, it's pretty much like an airship. They can get really big. Yeah.
That's wild to me that they're so thin and that big at the same
Mm-hmm.
time. Because yeah, I imagine you need like I'm not sure about how the density of the atmosphere changes as you get higher, but it definitely gets less dense, right? So whatever amount, I don't know. You might need some special kind of helium or something that's
You are going in the right direction. So what
yeah.
ends up happening is the atmosphere, of course, gets a lot less denser as you go up, and so your balloon kind of keeps inflating up. And at its fully inflated stage, it's as, if not bigger, as big as a football stadium. And so what you do is you underinflate your balloon purposely on the ground, such that as it rises up, it keeps on inflating and reaches its maximum size, such that it doesn't like tear up or there's a leak or something like that. So yeah, this the whole loads of techniques that ballooning people apply just to make sure that their balloons don't tear up. But I'm kind of diverting from the science that I am planning to get into. Is so yeah, why do this? Again, as I mentioned, A, you can access high frequencies, and B, you can cover up those patches in the earth that you otherwise would not be able to, because your balloon is free to move. Uh, so why high frequency matters is because the angular resolution that you see on the sky is a function of the wavelength that you're observing, right? And the diameter of your dish. So lambda over d. That's how the angular resolution is. Now, the diameter of the dish you can only make a dish that big enough on Earth without facing mechanical problems, right? The largest dish that we know on the ground is 100 meters. That itself is massive. Like that's in Green Bank in West Virginia. That's the 100-meter GBT dish, and that's already
Oh yeah,
big. Mhm.
Felix worked out there for a bit, right?
That is right. Yeah, my colleague Felix, he went there for a summer school. And yeah, that's a massive dish.
Yeah, and that's again coming back to the black hole famous black
Mhm.
hole image, right? Like you can't make dishes that they wanted to image a black hole, but
That's right.
you would have needed a dish the size of the Earth, and we don't have the technology to build a giant Earth-sized
Yep.
telescope floating in space. So you make a
hmm
bunch of tiny telescopes and kind of make like a discrete disk out of them, I guess.
Yeah, an
And that's
array of it.
yeah,
hmm
exactly.
That is exactly right. So yeah, these black holes, they're of course like insanely far away, and if you do the math, if you want to image a black hole that is that far away, if you just plug in those numbers in that theta formula that I said, the angular resolution, you'll quickly notice that the diameter of the dish you require is larger than the Earth, and that's not physically possible. And hence, you need such a technique called VLBI, where all of your dishes are placed as far as possible, and then you collect data observing the target at the same time, and you store those data, timestamping your data, right? So timestamping is extremely crucial in this aspect of the experiment. Is the reason why you need to timestamp your data to a precision of uh, 10 to the minus 12 picoseconds or even higher is because you would need to know when exactly those waveforms hit your dish. And only then you can compare with other dishes and stack them up together to make a image of the black hole, for example. Yeah.
Yeah, I just want to get into a little bit of the interferometer because the
Mm-hmm.
usually when people think of collecting data, we think let's say a photograph, right? The digital photo uses sensor where a ray of light come hits the sensor and give you the photo, an image basically. But interferometer works a little bit differently, where you need basically two sources and you interfere those sources with those data. And when, let's say you know exactly what those signals are going to be. I'm just thinking about the Michelson interferometers. You have the two lights that you know exactly how to interfere, right?
Sure.
And so if there's something in between there or something that changed in between, we can basically get out the profile, and then it would tell us information about what's out there. So basically, you take two sources, maybe subtract or do some mathematical function onto it. I think is that how it works in radio too?
Sure. Yeah, kind of similarly. So, radio telescopes, right off the bat, just to mention, they are like single pixel cameras. So, you cannot think them as like digital cameras that you use to take images of the night sky. So, what they do is they record the intensity of radio, the brightness intensity of radio light coming from just a patch in the sky. So, they are like single pixels. Those pixels basically give you how much of radio light intensity you're collecting. Now, the way you make an image is basically you scan your telescope throughout the patch of the sky, and you slew your telescope left to right, up and down, and stitch all those pixels on top of each other, and then you get an image of, for example, a radio galaxy or whatever you observe, right? So that is how radio telescopes work. And most of these things are diffraction limited, right? So now, when you have two radio dishes separated by some distance, which is usually what we call as baseline, which is the distance between the two radio telescopes, so you still have one source. You still have that source like kind of reaching the radio telescope. Now, what will happen is one telescope will see the source a little bit earlier than the other. So just by the virtue of fact that they are kind of pointed at the source. So imagine a wave of light coming from the source hitting one telescope faster than the other. And you can actually, by doing some clever geometry, you can actually quickly figure out how long it takes for the light to hit the other dish. And then since you know that time, you can go back and use that time to now effectively emulate a big dish as size as they are separated, right? So that is how interferometry in radio light works. So all you need to know is that the time delay it takes the signal to reach the other telescope.
Right, because it essentially is a transformation, right? If you think about it, instead of going to the flat surface, like everything's flat, but because it's a dish, you can calculate the time difference. And if you basically make probably some kind of matrix transformation, right? Like basically a function that transform that back to something that looks flat. I think that's right. In photography, people correct distortions and stuff because the light rays, if you know the profile of the lens, you can correct those distortions and you get a proper picture.
Exactly. So that is kind of how interferometry in radio works. And this is precisely the technique that a lot of the nice interferometers on Earth are using. So for example, we have one in Chile sitting on top of the Chilean plateaus called ALMA, right? That is a beautiful interferometer. It's doing high frequency radio astronomy, giving us excellent images of like really far away objects. Then you have what the EHT or the Event Horizon Telescope does, that is the collaboration that took the black hole image, is basically it just uses all of these beautiful radio telescopes that's out there, and then again, as I said, observes a same target and like collects data. Now, what I want to say is what I would like to take this discussion towards is how like my research with respect to my balloon telescope can help in here, right? So as I said, like accessing high frequencies, what that allows you to do is also push up the resolution, which we are kind of limited by right now, right? So you cannot make the Earth any bigger. We already have the telescopes at its maximum possible separation. I mean, you can't build anything that's much farther than that. The only best option is you could go to space and build a telescope on space. But again, as we all know, that's expensive, time consuming, and I mean, there are missions that have already done this, and there are missions that will do this. But doing from a balloon is a quick way to show, hey, it's possible from a balloon. It's much cheaper, and we can replicate this and include more balloons, right? So it gives you access to higher frequencies and it fills up in those places. So what we could do, the interesting part, maybe much down in the future, is we can actually help the Event Horizon Telescope take high resolution images of black holes. The exciting part about that is right now what we see in the black hole image is this blobby structure, circular structure. And we kind of have an idea as to what that is. That is basically the emission disk around the black hole that we're seeing. But the resolution is still not high enough to do more interesting science. So for example, the next target for astronomers is to actually study the photon ring around a black hole. Now, what a photon ring is that's the closest orbit that a single photon of light can take just revolving around the black hole. And that's actually much closer to the emission ring. So in the future, you might see a higher resolution image of the black hole, where you can also see a thin ring of light just outside the event horizon of the black hole, or the point of no return for the black hole. And that is super exciting because now you can probe in that region of space-time that otherwise was not possible because you didn't have the high resolution or the sensitivity to do that. So yeah.
Right. And all these cosmologists made all these models can now have some evidence.
Exactly. That's right. You can constrain GR, general relativity, even more. You can constrain the parameters of GR even more. And who knows, maybe that is where the answers to quantum gravity is lying. Maybe the closer you probe to the black hole, that's where both gravitational and quantum effects are increasing. And maybe that's where you'll find a lot of answers. Maybe. You never know, right? So the goal is to probe as close as possible, and photon ring observations will be the key for that. And for that, we need higher resolution. And so what I feel my research and where I see myself taking forward is building these balloon telescopes and really having the technology to access super high frequencies, so greater than 600 gigahertz, 900 gigahertz maybe, and just probing those really fine regions around the black hole to study the photon ring. So that is kind of my plan in the future, but yeah, that's just
so
long work.
More about what you do, like, because I know a lot of astronomers, their work is a lot on the data analysis part. Sure. But I think yours are on more instrumentation. But do you also work with data and analysis too?
Yeah, for sure. Yeah, so right now this project is basically being led by just 2 graduate students. So which means that you get to wear all kinds of hat. You get to wear an engineering hat, you get to wear a software developer hat, you get to wear a physicist hat. So you can literally delve in all of these avenues while building the project. So I personally, I have a background in electrical engineering, which really helped me. But I also wanted to do astronomy, hence the shift for grad school. And what that means is I not only get to kind of design the experiment, like design the science behind the experiment, right? What kind of radio telescope you would need, what kind of radio backend you would need, so on and so forth. But I also get to build that thing in the lab, assemble everything, write the software for it, collect data, analyze that data. So the whole process, you can have a hands-on, first-hand experience over it. So that's really cool. So I get to build a lot of the subsystems for the telescope. For example, I was in charge. I'm still in charge in building the back end of the telescope. So the telescope basically records the raw voltages that is coming in. So it converts the electromagnetic waves into raw voltage values. And I get to record that on an FPGA, store that data. I'm also handling the timing as aspect of the experiment. So as I said, you need to timestamp your data. I'm also working towards that. So yeah, a lot of these individual subsystems that you get to work on hands-on. So that's a lot of fun.
Wow, it sounds like a gargantuan amount of work for two people.
That's true. It is a lot of work. Of course, like we have been getting a lot of help from a lot of undergraduates who work with us in the summer. So that kind of really helps us. Our supervisor, who is also the PI of the project, Professor Laura Fizzle, she puts in a lot of input, helps us, guides us. And then we have super nice collaborators outside who also keeps guiding us. But yeah, the
Right.
work,
You said like with you not having to build a balloon is probably helped, right?
that, yeah, for sure, that helps a lot. Yeah.
Can imagine that would be brutal if you had to actually do the balloon yourself. You'd
Yeah,
need a
I
whole
don't
other like team for that, pretty
exactly.
much.
Hmm.
But I was wondering, so the goal is the black hole imaging, but is there anything else that you're interested in, or is that just like step one, and then you'll worry about that later?
Yeah, so step one is not even the black hole imaging.
Hmm.
Step
Yeah.
one is just showing that by the way, we're doing this at K band. So in radio astronomy jargon, that's 22 gigahertz. So that is the frequency that we're observing right now. You might ask why that frequency is just it was easier to find components on that frequency. So we brought a lot of the components off the shelf and built it in cheap. So the thing with radio astronomy is the higher frequency go, the cost of the components go up. So we wanted to do it in cheap. We wanted to just show that, hey, it works. So this frequency. And so the first goal for now is just detecting fringes. Now, what do I mean by fringes is basically we want to see we are also applying time on ground-based dishes. So the 100-meter GBT that I said, we have applied on that. We have successfully got time there. We will be also applying to a lot of other ground-based telescopes, and we've also got time on that. So the idea is when our balloon telescope and the telescope on the ground sees one thing together, can we see that correlation between them? Can we see that strong signal where they interfere positively with each other? That's the goal for now. If we see that, that's a success. If we don't, then yeah, that's a different story. We need to dig in deeper. But yeah.
So I want to elaborate on how these things work because before I came to university, I thought people in the astronomy department just have a bunch of telescope and they
Mhm.
just collect data on site or you have big telescopes somewhere. But apparently, how it works is because there are these huge telescopes that take billions, hundreds of millions dollars to make, and there are very few around the world. How it
Mhm.
works? People put up a proposal to have like some time on that and say, hey, point this telescope at
Yeah.
this place in the sky and give us your data. And I
Mhm.
heard there's will be some depends on the agreement to be like it will be for you for 1 year, and then it will share for everybody for the rest, right?
Mhm.
Like, can you tell me if I'm wrong of how that
Oh,
works?
for sure. You're kind of in the right direction. So these radio telescopes or even optical telescopes, for that matter of fact, they're extremely competitive to get into, right? So there will be astronomers from all over the world writing proposals to to the committee there to allow them some time on the dish, right, so that they can do their respective science. So for us, we applied for this weird thing when we were like, hey, we'll only observe something when our balloon launches, and they hadn't heard something like this before, so they were pretty puzzled. But I think our proposal was good enough that they gave us some time. But how this works is you propose time, and they will decide if your science is worth it or not. And then if the things that if it is, then they will give you some amount x amount of time. And mind you, the more time you request for them, the difficult it gets for them to give you time, because there are like thousands of astronomers, if and maybe more, applying for that same telescope, and maybe they also have pretty good proposals. But in the end, you only get, let's say, 10 hours, 20 hours of time, and you have to do your science in those 10 and 20 hours. And once you're done, they give you back the data to you, and then you can take back the data and analyze it.
Right. One of the challenge I find these things because like everything is moving all the time, right? It's dynamic. So
Yep.
if you can, it's hard to like, okay, I'm gonna build a new instrument. I'm gonna compare the data from the past, but you can't get the new data because that thing is already moved, right? So,
Yep.
or are there any method that are like that you can look back? Let's say, okay, this was the data recorded 20 years ago. Or we can still look in that same object. We suspect the same shape of data, or are they dynamically changing throughout the time?
So you're right. So of course the night sky changes. I mean, the position of everything on the night sky changes every night. But if you look at a long span of time, relatively the positions of the stars do not change that much respect to us, right? So that is why you don't need to worry too much uh, about like finding old data and like analyzing the data, because yeah, I mean things don't change that much. So it's not a big of a problem. But what the problem here is each second the sky is rotating at some speed, and you have to design your telescopes to actually track that object, and that can be tricky, because imagine moving 100-meter big giant dish, metallic dish, uh, at such speeds. That is where the trick challenge is actually. um, Over the long period of time things don't move that much, so you can still have your stuff on the sky where it was 20 years ago.
I
Mhm.
see, because there are those telescopes that you can buy that follow specific star throughout the
Uh-huh.
night and stuff.
Uh-huh. Uh-huh. Yeah.
So I'm not sure if Feely has any more questions, but for the sake of time, I wanted to move on and ask you about kind of what got you into science and physics and astronomy. I know that you have a YouTube channel where you do science communication, and I had a
That
quick
is
look at
right.
that, and it's pretty cool. So
Thanks.
like what got you into science in like high school or even when you were a kid, right? Like how did you what made you decide to pursue it, I guess?
Sure. Yeah. So I think my kind of story is pretty typical, as you would hear from folks who also do astronomy. Yeah, I think what happened with me is in my, I think, seventh birthday is where I received this encyclopedia. I still remember the name of the book. It was called The Encyclopedia of Space and Our Moving Earth, and that had like pictures of planets and the moon and the sun and dusty beautiful nebulae, and that kind of got me really hooked. And as a 7-year old, all I did throughout the next few months was just stick to the book and just turn those pages, even though I didn't understand anything. And I think growing up, that just got stuck in me so much that I knew from then that if I did something, it probably would be something in astronomy. So I really didn't have that dilemma growing up. Hey, I'm stuck between these two choices. I always knew I would do astronomy in some form, but the path to astronomy was not straightforward. It's because I did my undergrad in engineering, because it just was the lack of knowledge as to how to proceed to do astronomy in a conventional way. So I got into engineering, and then I did 4 years of undergrad in engineering, and then moved to astronomy. So now looking back, I think it was great. I think now I have a technical knowledge that I can use and make stuff, and yeah, it's fun.
Oh, it's kind of like, if you grew up in Asia, you have a lot of pressure to go
Sure.
into either engineering or
Or medical, I
medical
think
field.
these are the two,
Yeah,
yeah, streams there. Yeah, your parents kind of
yeah,
expect that. I think I fell into the same trap, honestly.
yeah.
So
And
yeah.
the thing about books is like when you were young, books are basically
Mhm.
doors to another world, right? Like because like outside for some people it's kind of a little boring, but when you open these books and yeah, I
Yep.
find that there are two types of physicists, and one is looking out, the other is looking in. And
Hmm.
to me, I never really got into stars and planets or astronomy because like I look up like, well, I can't see much. But if I look in, there's so many things like crystals and
Hmm.
nano, quantum and stuff that's really fun. And yeah, and to me, those two things are equivalently interesting. But
Hmm.
I'm just not that guy to do astronomer, which is interesting to hear from you who like, well, this is your thing. Like were you how do you get into this like balloon stuff? Was it your goal to do instrumentation, or Like, was it
No.
like, how do you get into these balloon
Yeah,
astronomy?
fair. I knew that I wanted to do something with instruments, as in I didn't want to do like typical theory-based thesis or theory-based work, because I knew I would get bored after a while. So I needed to get my hands dirty with instruments. But ballooning just kind of happened because so I was applying to a lot of grad schools, both in the US and in Canada, and I found my supervisor Laura Fissel's past work. She worked on this project called BLAST, which was a sub-millimeter telescope from balloon, making beautiful maps of star-forming regions, and it was an excellent mission. And that kind of got me hooked to this whole concept of ballooning. And then I started digging through it while I was applying through grad school, and that got stuck. I'm like, hey, you can get really good science from a unusual platform that is much cheaper than space, but also very exciting. So, and it so happened that me and Laura kind of connected with each other, and I think, yeah, and that's how we kind of like went ahead. But so I did my master's with her, kind of developing a lot of techniques in radio instrumentation and analysis. So yeah, that's how it kind of went on from there.
So was the transition difficult from engineering to more like astronomy and physics?
Sure. It was difficult initially because yeah, I had to take up a lot of core astronomy based courses when I went in, and as an engineer, you are involved with physics, but not in the very typical sense that a physics honor student would, right? So yeah, that transition was a bit difficult, but since I was so interested into it, I didn't feel that pressure. Uh, so it kind of went on together with everything else that was going on with me. But yeah, yeah, but that was a lot of work. I'll be honest. It was a lot of work, especially in my master's, where I had to take up 4 courses, all core physics heavy, astronomy heavy courses. That was a bit of a challenge, but I think I did okay, and I left everything, and
So
yeah.
there's this one loaded question we ask every guest. So
Mhm.
what are your hopes and dreams? Who do you see yourself being in the future? Do you see yourself being more like an astronomical engineer? Do you see yourself become a professor, work in industry? Do you still want
Sure.
to work in radio astronomy or expand yourself into other types? Like,
Mhm.
what's your hopes and dreams?
For sure. I think for once, I definitely see myself getting into academia even more as I travel down this path. I think what I want to do is really make these novel techniques of doing astronomy from balloons more accessible, and do it at a larger scale such that you can actually do meaningful science more easily. I want to take it to that level where you can have bunch of balloon telescopes floating around and taking simultaneous images of black holes. And I think my kind of main goal is to sort of focus on constraining the photons around black holes. I want to know what's going on around black holes at that level. So that is where I honestly feel my research would like to go. But there are other things that I'm also super interested is I'm super interested in science communication. I also want to make all these concepts easier for others to and kind of inspire and excite others, right? Especially folks watching videos from remote part in Asia or in Africa, or even like people all around the world in general. I want to simplify this concepts because when a new exciting research comes out, there's this crazy pop culture science headlines that will come out, which is not true. But then is also the other side is super technical jargony words that people don't understand. I want to be the bridge between these two, where using my knowledge, I can simplify all of these technical terms for everyone to sort of enjoy together. So that's kind of my goal going forward, actually.
Yeah, I think we have some similar goal in that sense because like this podcast can go
Mm-hmm.
extremely detail. Well, not
Mm-hmm.
that much detail because it's in a sense we don't have a board we can write and do the math, right? But sometimes we have a guest come in talk heavy math stuff and physics stuff. But
Sure.
we can also try to we can realize, when I'm editing it, it's like, whoa,
Mm,
yeah, it's pretty
yeah.
heavy, and some
Yeah.
we want to like even the concept of say like interferometer, and sometimes when because we have been dealing with this a lot, it seemed natural to us. Oh, it works like this. But I think for people outside the field, it's just something that's completely foreign. And that happens in almost every field, right? If you go into any advanced research, and they're going to have their own jargon and terminology that they always use. And it create these barriers, and people like to say, it's like these things gatekeeps a lot of people. And I think
Exactly.
especially for children or people who wants to go into science and they see this extremely difficult stuff, they might be a little discouraged, or some maybe encouraged to fight it, like Liam, for example. But I think science communication has become extremely important these days. And the fact that the tools that we can use to make those are so simple. Everyone now, almost everyone has a phone, at least in a very, even basic phone, you can record. And if you can develop your a communication skill, I think is extremely good. So with that, would you like to plug your YouTube channel on what you do? And I see you
For
have a
sure.
beautiful
Yeah, that'd be
website.
nice. Thanks for allowing me to do this. But yeah, I have a small channel up on YouTube. It's by my own name. So youtube.com/mayukh.bagchi. But what I do there is basically just like talk about astronomy in general and break down any exciting news that's coming up in astronomy, cover any research paper that shows up in the archive that is maybe complicated for everyone to understand, but I try to simplify that, so on and so forth. And my main goal, again, as I said, is to sort of simplify a lot of these heavy technical things for the mass in general to understand and appreciate astronomy even more. So yeah, feel free to watch it. And thanks for actually letting me plug this in.
It's all good. We need more people doing this.
And in the description of the episode, we'll put like a link to your website and your YouTube channel and whatnot there.
That's very kind. Yeah, that'll be super, super cool, super helpful.
Yeah, I hope you continue to do this. I know our guest before, well, early guest Parisa, she also started a YouTube channel. I think she has a vlog on her stuff, where go to do astronomy events or.
That's one thing I've noticed actually is the astronomers do a very good job of communication, even at McMaster. There's a prof who talks to my supervisor every so often, and they brought up the point that like, in the department there's condensed matter, there's medical physics, there's astronomy, there's a few other things, neutron scattering, but out of all the different fields, all of the science communication is done by the astronomers.
Yeah, and I think that there is a reason for that too, because I think one of the primal curiosity of human is looking at the sky, where it's not so obvious when, like, you're gonna look like nano fabrication, like it's not really relatable when you're young too, right? And so I can see that a lot of astronomers, how they get started were from those outreach, from those media. So they kind of want to propagate it along. I think that's really common sentiment where a lot of maybe our field is quite like, yeah, we are gonna do this niche stuff because we like it.
But it's yeah, and I don't know what it is, but like, yeah, so like McMaster, the astronomers are really good. They do a lot of science communication. It's like, it's not even that, well, it is, they're very good at it, but the people in the other fields just have no interest in communicating their work. I know like these quantum gravity guys, and or not even that, but like, condensed matter people or medical physics people, they just want to do research and hide in their office or lab. Like, none of them have any, and I shouldn't say none of them, a lot of them are interested in it, but they just don't do it. And the ones who aren't interested, they don't care. The astronomers are
Yeah.
very interested in it, and most of them are, from what I've seen. And I think the other
Yeah.
fields need to take note from that.
So if you're in those fields that Liam mentioned and would like to refute those claims, please come on the podcast and say it to Liam's face.
Other fields are included. Or sorry, other fields are available.
Well, anyways, I think we had a great discussion. So before we get Patrick to tell us how to reach us and how to find us on all the platforms, is there anything else, Liam?
Oh, I was going to bring that up, that people may have noticed Patrick has not spoken a word since the beginning, potentially. So I just want to say he didn't make it to this episode. He had a work emergency he had to stay for. So he will tell people how to reach us through the magic of audio engineering. And he'll tell you a story about something.
Yes, something astronomy.
Patrick, we missed you. I don't know if this is the first episode we were missing one of us. I think it might have been the first or the second. I can't remember, but
Yeah.
So, if you've been listening to this episode, you may not have heard me throughout. Unfortunately, I had to record asynchronously, but that's okay. I'm still here to tell you how you can contact us. So, you can find us through Gmail. We are hyperthesispodcast@gmail.com. You can send us questions as well as questions you may have for our guest. You can also send an interest if you want to be a guest on the show. If you're an expert in your field, we would love to hear from you. And we especially love having different graduate students on the show and young researchers as well. You can also find us on Instagram. We are at the Hyperthesis. Go ahead and check our page out for updates. Give us a follow. And you can also DM us there if you have questions or if you would, again, like to be a guest on the show. If you're listening to us, congratulations, you found us. We are based out of Spotify, but we are found on pretty much whatever podcasting service you may use, including YouTube Music, Apple Podcast, Audible, just whatever you use, you can find us, share us, give us a rating, and subscribe. So really contact us through whatever means you'd like. And you can also find us on YouTube. We're working to get this new season up and running on YouTube. We're very excited for that. So feel free to share us over there as well and put us on in the background too while you're working, let's say. So getting into today's story, I'm going to keep this a little bit short. Again, it's asynchronous, but it wouldn't really be about a scientific person, but we'll outline a timeline of one of the best inventions in the world. In my biased opinion, but I'm sure our guest shares the same opinion. The story will detail the development of telescopes, tracking the records from Galileo's time and even possibly a little bit before to the largest telescopes on and off Earth today, along with some future plans for some very large telescopes in the near future. First, we will start all the way back towards the humble beginnings of the telescope before we explore the giants that they have become today. The earliest recorded, generally uncontested instance of a telescope comes to us from the Netherlands, where Hans Lippershey attempted to patent the device in 1608. It is possible that the patent was not accepted because the invention of Lippershey already existed and was commonly available, especially in fairs and other, as kind of an amusement or toy. Nevertheless, the design started to spread more rapidly across Europe, where just a year later, Galileo improved the design and used it for astronomy. And of course, we won't go too much into Galileo. You can listen to our other stories about him. But given that Lippershey was an eyeglass maker and many telescopes followed the same model, these early telescopes were made from a convex objective lens. So convex is the one that kind of it pokes out instead of caving in. This is the same type of lens as a magnifying glass. It was proposed that a more powerful telescope could be made with a convex lens, so the one that kind of caves in, by none other than Johannes Kepler in 1611. By 1655, Huygens was able to build this Keplerian telescope, which utilized a compound eyepiece. Now, while glass lenses were fine, Newton is credited with the first reflector telescope, which used a mirror instead of a lens to focus light onto a flat mirror through which an observer could look. Only 4 years later, in 1672, Laurent Cassegrain designed a secondary convex mirror that reflected light from the main convex mirror into a hole within that main mirror. So it just kind of reflected it backwards, and then you could look through that hole. Now, by this time, telescopes were limited in size to only a couple of inches in diameter at the most. And the larger the telescope, the more light that can enter it, and so the more that you can actually see. Glassmaking was definitely a limiting factor, and I just want to focus on glassmaking for just a few minutes. The first really big advancements, aside from actually having clear glass and consistently clear glass, was the creation of the achromatic lens, as we've discussed before, and Liam has talked about many, many times. And I'm sure if you want to hear more about it, just send Liam a DM and he can tell you all about different wavelengths of light will refract differently when going between two media, and achromatic glass solves the issue of traditional glass by bringing those wavelengths closer together after passing through them, limiting the amount that the color actually splits. This allows for a shorter and less complex telescope that uh, is able to automatically correct for this chromatic aberration, as it's called. Now, achromatic lenses are attributed to Chester Moore Hall from 1733, but he didn't really publicize it. At this point, telescopes started going from inches to feet in some cases. John Hadley was able to produce larger parabolic mirrors before the use of achromatic glass, and even larger mirrors were produced by Leon Foucault of the pendulum fame by using a silvering method. And now it's important to note that a lot of the mirrors that you might see in your bathroom, their reflective surface is behind the glass, but that can lead to even more chromatic aberrations and distortions. So people found it even more important and useful to put the silvering on the front of the glass, which makes it a bit more delicate to work with, but produces a much better result. While mirrors developed and failed at some points, there are some really interesting situations of that, even in the more modern day. The era of refracting telescopes was really among the worst. So in the 50-year span before the 20th century began, lenses between 60 and 100 centimeters were being constructed. But of course, you start to reach limits. In 1897, the Yerkes Observatory debuted a 102 centimeter diameter telescope. Now, the title of largest telescope didn't last too long for refractors, and it really kind of stopped around that 1 meter mark. With the new and improved reflector telescopes, they were able to start measuring at 1.5 meters at Mount Wilson, 2.5 meters at the Hooker telescope, and 5 meters at the Hale telescope in 1948. These reflectors were superior to the refractors, with issues of aberration solved through the shaping and coating of the mirrors in specific ways. They were also able to use some passive adjustments in the mirrors. And as the 20th century moved on, larger telescopes in the 4-meter range were produced and installed in places like Mauna Loa in Hawaii and the Atacama Desert in Chile. I do want to highlight that both of these areas are quite high, and the higher you go, the less atmosphere you have to look through. And then there are also conditions like in the Atacama Desert where you have a lot of clear days, and the same thing in Mauna Loa, Hawaii, where you're high enough above the clouds that they don't really interfere, and you're able to get better imaging. These telescopes still rely on very precise and expensive glass making, but they were quickly outclassed by a field known as active optics, where mirrors can actually be adjusted. So there are some new telescopes nowadays that are actually able to create tiny distortions within the mirror to account for atmospheric corrections or even through manufacturing defects. But these types of telescopes are manufactured very, very accurately. The introduction of computer control aided this as well, allowing for a new generation of telescopes in the 10-meter range to be produced in the mid-90s. Now, in terms of optical telescopes, which we'll focus on here, the largest is yet to come. It's worth mentioning the Hubble Space Telescope, which is an optical telescope based in space in orbit around the Earth. It was launched in 1990, and it is still in operation to this day. Now, its dimensions are about 13 by 4 meters, so it's about the size of a school bus, which is small in terms of the current telescopes that we have nowadays. But its main telescope is a 2.4 meter diameter, what's known as a Ritchie-Chrétien reflector. Finally, our kind of largest space optical telescope is something that we've talked about before, and it's the James Webb Space Telescope. Now, this is an infrared telescope, so it's not looking at visible light, it's looking at infrared light, but its main telescope is known as a Korsch telescope, and it has a 6.5 meter diameter, and it's actually not orbiting the Earth. It's at a Lagrange point, kind of outside the Earth, but still adjacent to it in a way. So we have some large space telescopes, and we have even larger radio telescopes, of course, I won't get into. But there are other large telescopes like on the horizon, such as the extremely large telescope, which is, well, extremely large, with an aperture diameter of almost 40 meters. But there are other large telescopes too. So one of the largest optical telescopes operating today is the Gran Telescopio Canarias with a 10.4 meter aperture. But other planned ones are the giant Magellan telescope, the 30-meter telescope, and large binocular telescope, which will use 2 smaller mirrors, but combined that makes a decent size. So there are a lot of massive telescopes in the works, and they're working on getting these telescopes kind of planned and zoned even for, because there's a lot of controversy over placing them in certain areas, but a lot of exciting things. Chances are we wouldn't see the highest telescope in a balloon, but who knows?
Well, thanks, Mayukh. I think it's
Yeah,
been a
no.
very productive and fun discussion. So
Mhm.
thanks for coming.
Yeah, no, it was equally fun to speak here, and then thanks for doing this. Actually, I think it's again, as you said, it's really important to bring up science communication and open up these on all of these platforms that everyone hangs out on, Spotify included, right? So I think that's a great initiative, and you have to be here, and hope to be in the future as well.
All right. Thank you.
Yep.
Take care.
Yeah,
Yeah,
thanks.
bye.
See you, everybody.
So, yeah.